Welcome to my talk about martingale-optimal transfer duality. My name is David Proemel. I'm from the University of Mannheim, and I would like to talk about a joint work with Patrick Chiridito, Matti Kielski, and Mete Soll. So martingale-optimal transport is heavily motivated by mathematical finance under model uncertainty. So please let me first remind you or recall for you the classical mathematical finance framework and how martingale-optimal transport arises in there before coming to the results about duality. So in classical mathematical finance, one likes to model the price evolution of some assets by a stochastic process on an underlying probability space. And then if the market or the model is arbitrage free, it is known by the fundamental theorem of asset pricing that the set of equivalent martingale measures is non-empty. Right? So there you already see that martingale measures arise. One of the fundamental questions in mathematical finance is to find arbitrage-free prices of options. So options here are just random variables. And there are many approaches to this problem, and two main ones are presented here. The one is pricing by superhedging, which is just finding the minimal initial capital I need to invest or trade in the market so that my terminal wealth is higher than the option side. And the other one is pricing by martingale measures, because we know the price has to be consistent with these martingale measures. So we define the price by martingale measures as the supremum over all martingale measures, and then we take the expected value with each of these martingale measures. And these two approaches lead to the same price as stated by the pricing hedging duality. So the price of superhedging by superhedging is equal to the price by martingale measures. And now over the past 20 years, there was a lot of research going on to understand these fundamental results in a robust way in order to include model risk or model misspecification. And today I would like to try to understand this pricing hedging duality in a point-wise model-free setting. So what I would like to do is I would like to choose omega as a subset of the scorecard space, and these are all the price trajectories I would like to consider. And the process S is now just the coordinate process on the scorecard space. So there's no probability measure involved anymore. And the underlying filtration is the right continuous version of the filtration generated by the coordinate process S. Well, and now in this row one setting, it's commonly done that there's the additional assumption that the vanilla options are so frequently traded that they are considered as an input parameter. Because they are currently, or nowadays, so frequently traded on the market that they are part of the underlying financial market. So what I would like to do, assume that there's the class GS of all financial European option of this form here. So function f applied to the price at time terminal t. And if I have all the prices which are here normalized to 0 of this financial option, I know the marginal distribution by Braden-Litzenberger's formula of the maturity, so of the price process at time capital T. So the price by martingale measures in this robust setting changes now to taking the supremum over all those martingale measures which are consistent with the observed option prices. And this is led to the notion of martingale-optimal transport, because here we face a martingale-optimal transport problem because we want to transport the mass from the current observed price to a marginal distribution along all martingale measures in this set. So this is our price by martingale measures. And now to come to the price by super hedging in a robust way, we need to be also a bit careful because we have no reference probability measure. And the simplest way to start with are indeed the simple strategies. So we take, as I said, we can buy European options. So we take a static position in the European option, and then we trade by using step function. So we trade only finitely many times. And the corresponding capital process, then it's just a Riemann sum, which is assumed to stay above some constant. And the super hedging price, using this notion of trading, is, well, as one expects. So I want to find the minimal initial capital process, the minimal initial capital, so that my trading in the market plus the payoff of the option super hedges the option side. And here there are two new features in red. The one is, of course, the option as discussed. The other one is I want to hedge for every omega in omega. So pointwise and not only almost sure. The first duality, the martingale-optimal transport duality in this framework was derived by Dolinsky and Sohner, showing that if my option psi is uniformly continuous with respect to the uniform topology, then we has indeed the pricing hedging duality. So the super hedging price equal to the martingale price. And this was then generalized in general other direction. But the question I would like to ask today is what happens if we consider less regular option? And unfortunately, with the definition of super hedging prices we just have seen, there is a duality. So let us understand what we have to change in order to restore the duality. So let's consider continuous options, so not necessarily uniformly continuous option. So if I take a reasonable class of super hedges, well, my super hedging functional will be convex, monotone, proper, and positive homogeneous. And then the moment I have some continuity property as lower semi-continuity, I always have a dual representation by Fenchel-Morrow theorem as presented here, which is given, so the dual representation is given by the dual elements which are dominated by the super hedging function. So this representation, this delta p, is just the subdifferential at 0 of the super hedging price. All right, so the issue, of course, even while this gives you a nice presentation, the subdifferential p, delta p contains not only countable additive measures, so not only probability measures. And the question is, how can we ensure that we have that the subdifferential at 0 are the martingale measures? And there are two main ingredients we use in this approach. The first one is we choose the suitable topologies on the space. So to be precise, we choose the regularized version of Jakubowski's topology on the scorecard space and the beta 0 topology on the space of continuous function. Because then it's known from functional knowledge that the dual pairing here consists only of countable additive measures. So we have already probability measures in there. The issue now we face, so by changing the topologies, is that we need to smartly choose the space of the class of hedges in order to have some continuity property now with respect to the beta 0 topology. And for this, we follow an approach by Vladimir Vovk, which goes as follows. So the static positions are as before. And the dynamic trading is now given by a sequence of simple strategies, which have a uniformly lower bound. And our capital gain process is now given by the inferior of simple gain processes. So we take a limit inferior, basically a closure with respect to limit inferior to define a bigger class of hedges. And the super hedging price is then as before, the minimum initial capital with the dynamic trading with this sequence of simple trading strategies and then the payoff of the option as before. And this allows indeed to prove that the super hedging functional P is continuous with respect to the beta 0 topology and the subdifferential at 0 is equal to the martingale measures consistent with the European options. So using Fenchel-Morrow's theorem, one has the pricing hedging duality for continuous option as well. And then by an approximation argument at the minimax theorem, one can extend this duality even to upper semi-continuous option as well. All right, so now what we have seen in the classical framework, that the duality holds for measurable option as well. So how can we extend this to measurable option? Well, since we are here in a basically capacity world, we need to rely on Jacquet's capacity theory. And this needs to requires us to use another closure of the hedges. So we take it for two closure of the hedging strategies we just have defined, and then we can apply Jacquet's capacity theory in order to get the pricing hedging duality or market-equal optimal transport duality for all measurable and bounded options xi. And again, as before, this part2 closure is strictly necessary, as one can come up with counterexamples showing that there's a duality gap if this part2 closure is not taken. So thank you very much for your attention. I hope you enjoyed the talk, and I wish you all a nice further conference.